Thousands of developers asked the same question. The AI answered. It was wrong. In 2023, a popular AI coding assistant suggested a specific authentication pattern to millions of developers. The snippet looked clean, it compiled perfectly, and it contained a subtle privilege escalation flaw that security researchers later flagged across dozens of independent codebases, all written by different teams, in different companies, on different continents. This is not a story about one bad AI output. This is a story about monoculture. When every farm plants the same crop, one pest can devastate an entire harvest. When every developer uses the same AI, one flaw can propagate across an entire industry. Silently, instantly, at a scale no human-authored bug ever could. To understand how serious this gets, we need to look at a historical precedent from outside software entirely. On August 14, 2003, a software bug in an alarm system, combined with a single, overloaded transmission line in Ohio, triggered the largest blackout in North American history. 50 million people lost power. The cause was not 50 million separate failures. It was one shared vulnerability in a tightly coupled system. Now let us map that same structure onto modern software development. AI coding assistants are the new shared infrastructure. GitHub Copilot, Cursor, Amazon Code Whisperer, and similar tools now account for a measurable fraction of all new code written in the world. These tools share something critical. They are trained on overlapping datasets, they converge on similar pattern libraries, and they respond to similar prompts with remarkably similar answers. How much code are we actually talking about? A 2024 GitHub survey found that developers using AI assistants reported writing code roughly 55% faster. That speed is not neutral. It means a flaw that once took months to spread organically through Stack Overflow answers and blog posts now propagates in hours, wherever developers paste the AI's output directly into production. Let us be precise about what a systemic AI bug actually looks like. In 2022, researchers at Stanford published findings showing that nearly 40% of GitHub Copilot suggestions in security-sensitive code contexts contained at least one vulnerability. These were not random or diverse flaws. They clustered around a small set of recurring mistake categories: buffer handling, SQL construction, and insecure defaults. The key word there is clustering. In the natural, diverse developer ecosystem, bugs are scattered. They're idiosyncratic. They reflect each developer's unique misunderstanding. But AI-generated bugs are systematic. They reflect the model's consistent misunderstanding. That distinction is everything. A scattered field of bugs is manageable. A uniform field of the same bug is a single attack surface, enormous and exploitable. Now imagine an attacker who knows this. Instead of hunting for a bug in one company's code, they study the AI model's tendencies. They craft prompts designed to elicit the vulnerable pattern. Then, they wait. Within days, that same vulnerable snippet exists inside thousands of companies' production systems, all because developers trusted the same oracle. This is not hypothetical. In 2024, security firm Sneak documented what they called AI-amplified vulnerability spread, where the same insecure JWT token validation pattern appeared in over 400 distinct open-source repositories within a 3-month window. The pattern was traceable to AI tool suggestions. None of those teams knew the others existed. The stack goes deeper than just the code. Consider the infrastructure layers that AI tools now touch. AI assists with Terraform scripts that provision cloud architecture. It writes Kubernetes configurations. It generates Docker build files. It suggests CI/CD pipeline definitions. A flawed pattern at any of these layers does not just affect one application. It affects the entire deployment scaffolding beneath it. Let us return to the 2003 blackout analogy in more detail. That event had 3 preconditions: a tightly coupled network, a shared failure mode, and no circuit breaker that could isolate the damage in time. Modern cloud software has exactly the same 3 preconditions: tight coupling, microservices and shared dependencies; shared failure mode, AI-generated code patterns; no circuit breaker, no industry-wide mechanism to detect and quarantine a spreading bug. Here is something counterintuitive. AI models are actually quite good at writing code for well-trodden, well-documented problems. The danger zone is the edges: deprecated APIs, novel library versions, language-specific security nuances, and framework configurations that changed after the model's training cutoff. These edge cases are exactly where developers are most likely to ask the AI for help, and least likely to verify the answer. There is a term for this in ecology: genetic erosion. When a species loses genetic diversity, its capacity to resist novel threats collapses. Software diversity plays the same protective role. When different teams use different books, different forums, different senior developers, they produce different code. That variation meant a flaw in one place rarely matched a flaw in another. AI is eroding that diversity at an unprecedented rate. Now let us look at how a real cascade might unfold. Imagine a widely used AI assistant suggests a particular rate-limiting implementation for a REST API. The suggestion has a subtle flaw, and the concurrent load above 5,000 requests per second it allows bypass. 10,000 developers use it. 6 months later, someone discovers the bypass. But there's no coordinated disclosure mechanism for AI-sourced patterns. There's no common vulnerabilities and exposures entry. There's no patch notification system. The bug simply exists everywhere. The concentration risk compounds when you consider which cloud providers run the infrastructure these AI tools depend on. 3 providers, Amazon Web Services, Microsoft Azure, and Google Cloud, serve the overwhelming majority of global internet traffic. The AI coding tools that generate the code and the cloud platforms that run it share the same infrastructure backbone. A cascading failure that exploits an AI-sourced vulnerability could simultaneously affect services running on all 3. Some will argue that code review and testing catch these bugs before they reach production. That argument has merit, but it underestimates 2 things. First, AI-generated code often looks more polished than human-written code. It passes style linters, it compiles cleanly. Reviewers are psychologically primed to trust it. Second, the specific vulnerabilities AI tends to produce, insecure defaults, subtle logic errors, are exactly the kind that evade standard unit tests. Let us also consider the supply chain angle. The open-source ecosystem is already a known vector for cascading failures. The 2021 Log4Shell vulnerability affected hundreds of thousands of systems because a single logging library was embedded everywhere. AI tools now actively suggest pulling in dependencies. A model that consistently recommends a particular package version or a particular library pattern concentrates risk in exactly the same way, but across a far wider surface. So what can be done? Researchers and security professionals are beginning to outline responses, and they cluster into 3 categories: technical defenses, process reforms, and governance frameworks. None of these is sufficient alone, and critically, all of them require the industry to first acknowledge that AI-sourced code carries systemic, not just individual, risk. On the technical side, one promising approach is model diversity by design. Just as biodiversity protects ecosystems, using multiple different models from different providers with different training pipelines for different parts of the stack introduces variation that limits the blast radius of any single model's failure mode. No single oracle, no single point of convergence. On the governance side, the most urgent gap is a disclosure standard. Today, if a researcher discovers that a particular AI model reliably produces a dangerous code pattern, there is no established channel to report it, no obligation for the model provider to notify affected developers, and no timeline for remediation. The closest analogy would be discovering a vulnerability in a compiler, and having no mechanism to tell anyone who used that compiler. The deeper question this raises is about trust architecture. We have spent 30 years building a software security ecosystem: certificates, audits, SBOMs, penetration testing, bug bounties, all predicated on code being authored by identifiable, accountable humans. AI fundamentally disrupts that assumption. When 1 billion lines of code per year are generated by models, accountability becomes diffuse, and the tools we built for a human-authored world begin to fail. Looking at the trajectory, the risk does not plateau, it compounds. As AI models improve, developers trust them more. As developers trust them more, verification rates fall further. As verification falls, the systemic exposure grows, and as AI increasingly writes the next round of training data, code committed to public repositories, flawed patterns may begin training the next generation of models to reproduce the same flaws. A feedback loop. To be precise about scale, GitHub reports over 1.5 million active repositories commit AI-assisted code today. If even 2% of those share a single flawed AI-sourced pattern in a security-critical path, that is 30,000 production systems with an identical attack surface. For context, the 2021 Colonial Pipeline attack, which disrupted fuel supply to the entire eastern United States, targeted a single company. This is the copy-paste collapse in its final form. Not a single dramatic explosion, but a silent homogenization. A world where the diversity that made software resilient is quietly replaced by a single converging pattern library, authored by machines, trusted by humans, and invisible to every security tool we currently have. The next major cloud outage may not be caused by a failed server or a misconfigured network. It may be caused by 10,000 teams who all asked the same question and got the same broken answer. The 2003 blackout was eventually traced, investigated, and led to sweeping reforms in grid reliability standards. The North American Electric Reliability Corporation was strengthened, circuit breaker protocols were mandated, and alarm systems were redesigned. It took a catastrophe to produce the governance. The question for software is whether we wait for the equivalent collapse, or whether we treat the warning signs we already have with the urgency they deserve. The copy-paste collapse is not about AI being bad, it is about concentration. The same force that makes AI so powerful also makes the software world it touches more fragile. A single extraordinary tool, used by millions, trusted implicitly, producing identical outputs at machine speed, is not just productivity. It is a single point of failure at civilizational scale. We have built this kind of fragility before, in power grids and in monoculture crops. We know how it ends. The answer is not to stop using AI. The answer is to treat AI-generated code the way we treat any other shared critical infrastructure, with standards, with diversity requirements, with disclosure pipelines, and with the humility to remember that the more powerful the tool, the more consequential its blind spots. The next major outage may be AI-authored. Whether it cascades into a collapse depends on the choices architects and engineers make today.